Bismillah Rahman Rahim. Assalamu alaikum. So we are going to start lecture 3. The contents for lecture 3 are: first we'll study factorization methods and its different types, Doolittle, Crout, Cholesky, and example of all these three methods. Secondly, we'll study Gauss-Siedel method, an example to Gauss-Siedel method, and at the end, relaxation method with an example. Factorization method. So factorization method can be used to solve n by n system of linear equations. So the system in matrix form can be written as Ax is equal to B, where A is the coefficient matrix, X is the vector of unknowns, and B is the vector of constants. If A is a non-singular square matrix, then we can factorize A into product of lower triangular matrix L and upper triangular matrix U. That is, A can be written as the product of L and U. So above system leads to this Ax is equal to B leads to LUXB. So let this Ux is equal to Y. Then Ly is equal to B. Here Y is the intermediate vector. Once A is decomposed into lower triangular matrix L and upper triangular matrix U, then we can use Ly is equal to B to find the value of Y, which will be substituted in the equation Ux is equal to Y and will give the value of X, which will be the solution of actual system Ax is equal to B. These factorization methods are also known as LU decomposition method, and sometimes we simply call them decomposition method. So it might be noted that Ly is equal to B is the lower triangular system and can be solved by forward substitution, and Ux is equal to Y is the upper triangle system and can be solved by backward substitution. For simplicity, here I am considering 3 by 3 system. So this is coefficient matrix of 3 by 3 system in general form. So this is lower triangular matrix and this is upper triangular matrix. So this will end up into 9 equations. Since we have 3 by 3 system, so we have 9 terms this side, and when we're multiplying these two sides, we'll also get 9 terms here. By equating each term, we will get 9 equations. Whereas if you look on the right hand side, we have 6 unknowns here and 6 unknown here. So total we have 11 unknowns but 9 equations. So this is impossible to find 12 unknown values from 9 equations. So means we have to do, or we have to replace some of the terms in these LU decomposition methods. So now for n by n system of linear equations, we will have n square plus n total unknowns, but we will get only n square equations. So the extra n entries in the LU decomposition can be adjusted by replacing diagonal entries in one of the matrix with unity, which will make it unit triangular matrix and will end up in n square equations with n square unknowns, so we can find the solution. So there are different types of decomposition methods, but here we will consider only 3 main types. Doolittle method. If A is decomposed in the form of, if we replace, in fact, the diagonal entries in the lower triangular matrix with unity, we'll call it unit lower triangular matrix. So if A is decomposed as a product of your unit lower triangular matrix and upper triangular matrix, then this decomposition or factorization method is called Doolittle method. So this Doolittle method is also called only LU decomposition method or decomposition method. These are the 3 names we use for Doolittle method. So second method is Crout's method. So here lower triangular matrix remains same and we replace diagonal elements of upper triangular matrix with unity. So give it unit upper triangular matrix U. So if A is decomposed as a product of lower triangular matrix and unit upper triangular matrix, then it is called Crout's method. So third type is Cholesky's method. So if A is a symmetric matrix, then we have privilege to decompose A as the product of lower triangular matrix and its transpose, which will of course be upper triangular matrix. So for Cholesky method, A must be symmetric matrix. Here are a couple of assignments. So do pause your lecture and do these assignments first before you proceed further. So consider n by n system of linear equations in general form and verify the following equations for Doolittle method. When you will multiply L and U in general form and will compare with the general matrix n by n, then you will get these equations. So there are 4 cases, 2 on each. So if row number is fixed in U or the upper triangular matrix entries, then you will get this equation, and if you will fix the column number, you will get this. And for general greater than 1 means starting from 2, you will get this equation for Uij, and this is for Lij. And hence tell me what will happen if Ujj is equal to 0, since Ujj is dividing here. The second assignment is, so define and explain LUP, so with full and partial, and LDU methods. So what are these methods? So you have to define and explain these methods. Example. So first, Doolittle's method example. For Ax is equal to B, here we consider the matrix A as this one. X is the vector of unknowns and B is the vector of constants. As this is, we have to do with Doolittle's method. So we consider unit lower triangular matrix and upper triangular matrix. By multiplying these two, comparing and solving these equations, we will get lower triangular matrix as this one, in fact the unit lower triangular matrix, and the upper triangular matrix this one. So by using Ly is equal to B, we will get the intermediate vector as 6 minus 14 minus 54, and then we'll use Ux is equal to Y, which will give us x1 is equal to 1, x2 is equal to 2, and x3 is equal to 3, which is the required solution. Now, example for Crout's method. Here we consider this matrix A. So in Crout's method, L will be lower triangular matrix, where U will be unit upper triangular matrix. So multiplying these two matrices, comparing and solving for unknowns, you will get the following answers. So this will be your lower triangular matrix and this will be your upper triangular matrix. You have to do all these calculations. So please check all these calculations. So then by applying Ly is equal to B, this gives the intermediate vector as 5, 4 by 5, 3. So you will use Ux is equal to Y, this will give you x is equal to 1, x is equal to 2, x1 is equal to 1, x2 is equal to 2, and x3 is equal to 3, which is the required solution, or in fact the solution to the original system. Here's the example for Cholesky's method. So for Cholesky methods, A must be symmetric, positive definite matrix. So if you look at this matrix A, this is symmetric positive definite matrix. So look this row and this column. So if you take transpose of this A, it will again be A. So in this case, lower triangular matrix will be this one, and its transpose will be upper triangular matrix. Multiplying these two, you will get 9 equations in fact, but you have only 6 now unknowns, so you can easily find the value for these 6 unknowns. So what you get for this matrix will be this lower triangular matrix, and its transpose will be this one. So you can multiply and can cross check this. This product should be equal to this matrix. Using Ly is equal to b, this gives the intermediate vector as 1, 9, 3, and using ux is equal to y, it gives you the solution, which is 1, 2, 3, and this is the solution to the original system. So next, before we start, for the numerical methods to solve system of linear equations, we need a definition. So diagonal dominant system. A system of linear equation in n variables, which is denoted in matrix form as Ax is equal to b, will converge rapidly, and it ensures the convergence of this system of linear equations if aii mode is greater than equal to summation j from 1 to n, j not equal to I, modulus value of aij for all I from 1 to n. So what actually this means? A system of linear equation for which above condition, this condition is what? This is modulus of diagonal entry in each row is greater than or equal to the sum of diagonal moduli of diagonal entries in that row. If this condition is satisfied on system's coefficient matrix, then the system is called diagonally dominant system, and diagonal dominance will ensure the rapid convergence of the system. So it will help us in getting more accurate result in less number of iterations. So if you look at the example, look at this system. So this first entry is 8, rest 2 and 1, 3. So 8 is greater than 3. Here 10 is greater than 3, 1 plus 2. Here 10 is greater than 3 plus 1, 4. So this is a diagonal dominant system. But if you look at this system, here 8, 5 plus 4 is 9. So this is similar here. If you look at this equation, 9, 9, 18. So this is not greater than 1. So this system is not diagonally dominant. But if you look at the system, it is 8, 1, 1. So first equation is fine. 2 minus 1, 10. It's not fine. Similar with the third equation, it's not fine since 5 is less than 1 plus 6. But if you look carefully, if we interchange second equation with the third equation, so now this will be at second place, so this will be the diagonal entry, 1 plus 5 is equal to 6. So this is equation is fine now. And similar, this will be the diagonal entry for third equation, and you will get these two as 1 plus 2 is equal to 3. So this system is not diagonally dominant, but can be made diagonal dominant by interchanging equation 2 and 3. So the point is, some of the systems are diagonally dominant, some are not, but there are few which are not diagonally dominant but can be made diagonal dominant. So before we proceed for the numerical solution of the system of linear equations, please ensure the diagonal dominance of the system. If it is not diagonally dominant, then please try to make it diagonal dominant. If you can't, but there are still so many systems which cannot be diagonal dominant or cannot be made diagonal dominant, but you can do as many equations diagonally dominant as you can. Similarly, we can define diagonal dominant matrix. A matrix is said to be diagonally dominant if it satisfies the condition. This is the same condition as we discussed for the diagonal dominant system. So this is for the diagonal dominant matrix. So the first method, numerical method to find the solution of system of linear equation, we are going to study is Gauss-Siedel method. For simplicity, we are considering 3 by 3 system and we suppose it's diagonally dominant. So we have written this in general form. Then from first equation, we'll find the value of x1. From second, we find the value of x2, and from third, we find the value of x3 respectively. Then we get these equations. So an iterative technique can be for the value of x1 for k plus first iteration, we can use the previous, since for x1 we need x2 and x3, so we'll be using the previous iteration or the initial guess to find the next iteration for x1. But if you look at the second equation, to calculate x2 you need x1 and x3. So this x1 has already been calculated, so we're using the updated value for x1 and we are using this value previous guess for or previous approximation for x3. Now in third equation we need x1 and x2, so both have been calculated, so we are using the updated value of x1 and x2. So this technique or iterative scheme is known as Gauss-Siedel method. Now this is for 3 by 3 system. So I am here writing this for n by n system of linear equations. So the Gauss-Siedel method for n by n system will be written in this form. So here xi is the ith, which can be 1, 2, 3 up to any n value, unknowns value for k plus first iteration. We will be dividing this component into two parts. Since when I is equal to j, this will be the diagonal entry. So this is on this side. So rest entries, consider second row for 3 by 3 system. So if you look here, the x2 is the diagonal entries. So you have entries before the diagonal, you have entries after diagonal. For the first equation, you have all the entries after the diagonal, and for last equation, you have all the entries before the diagonal. So we have to write the general formula. So we'll be dividing this into two parts. Since I will be missing in second equation, x2 is missing, in third equation, x3 is missing. Similarly, in first equation, x1 is missing. So here ith component will be missing. So the terms will be before I. So this will be summation from j1 to I minus 1. Then I will be missing, and then full starting from I plus 1 to n. So for the components for this range, we'll be using the updated value, and for this one we'll be using, since we don't have updated value after I, so we'll be using these previous iterations or the previous guess. So to start with this method, we need an initial guess. So we usually start by taking x1, x2, x3 is equal to 0, but it's your own choice. So you can choose any of the value you want as an initial guess. So how close your initial guess will be to the exact value, so less iterations you will need to reach that. So अगर आप किसी भी जगह पर कहीं दूर भी उसको guess करते हैं तो it will take some more time, but it will be coming towards the solution. So क्योंकि system diagonal dominant होगा तो convergence rapid हो जाएगी उसकी और insurance आ जाएगी. So इसकी explanation के लिए example देख लेते हैं. So solve this following system which is given here, starting with 0 to all initial guesses and stop when you have 1 decimal accuracy. So above system is, if you look, is diagonally dominant. So for Gauss-Siedel method, from first equation you will generate equation for x1, from second for x2, and for third you will use x3. So we're taking different values of k starting from 0 to get the iterations for the solution. So for first iteration, put k is equal to 0. So this x1 will be 1.25, x2 will be minus 1.125, the x3 will be 0.9. So this calculation you can do easily. So pause your video here and check these calculations. And then for second iteration, you will get these values. And for third iteration, you will get these values. And when you put k is equal to 3, this will be the fourth iteration. And in fourth iteration, you will get these values, which are somehow, since I have to check one decimal accuracy, so I just write down these terms for 4 decimal places. So if you look, these all three equations, maximum error is less than 0.5 into 10 raised to power minus 1. So all the values are 1 decimal accurate. This means the whole system is 1 decimal accurate. So this is the required result. So the next method we have for the numerical solution of system of linear equation is the relaxation method. So this is an iterative approach, numerical approach for the solution of system of linear equations. So the basic idea behind this technique is to improve the solution vector successively by reducing largest residual at particular iteration. So what is this residual? Suppose xi is an approximation to the solution of linear system ax is equal to b. Then the residual vector with respect to the system ax is equal to b is expressed as ri is, so we'll check all the components on the left hand sides to the other sides, will make it to 0. So these terms we will call b minus axi, xi is the guess, will give you the residual. So we can calculate residual at each step. So this is for the ith iteration, so you can calculate at each step. So Ri is b minus axi, so this b actual solution is ax is equal to b. Take a common, so this is actually what exact minus approximated is the error. So this is the error, and Ri is equal to aei is called residual equation. So we take the following steps to reduce this residual to solve this system of linear equation by relaxation method. So initially reorder the equations in a way such that largest coefficient in the equation appears on the diagonal. So just recall, this is the definition for diagonally dominant system. The next step will be, so the system made the system diagonally dominant if it can be made. So if you cannot make the whole system, then convert most of the equations into the diagonal form, diagonal dominant form. Next step will be transfer all the terms to the right hand side of the equation to make left hand side 0. Then select these will be the residuals. So select the largest residual and give an increment to that residual as dxi to that specific term minus ri over aii. Then you will change the initial approximation or the guess to xi plus dxi, where dxi is the increment. So you will do this change to relax ri, that is to reduce this residual to 0. So you will continue that steps until your residual approaches to 0. So to explain this method, let's solve an example so that you can have better idea of this method. Solve the following system by relaxation method, and we are starting with x1, x2, x3 initial values as 0. So this is the given system. So this is not diagonally dominant, but if you look, if we interchange equation 2 and 3, we can make this system diagonally dominant. So this system is now diagonally dominant. So the second step was to transfer all these values to the right hand side to make left hand side 0. So this is your first residue, will be your second residue, and this will be your third residue. So we're starting with x1, x2, x3 is equal to 0. So you will get residue from first equation as 11, for second equation 10, and for third equation minus 15. So the largest residue is R3. So we'll find the increment as dx3 since this is in the third term. So this will be minus R3 over A33. So this is minus 15 over 8. It gives 1.875. So the new gas will be what? So since this is changed in x3, so x1 will remain same 0, x2 will remain same 0, and but x3 you will add this increment. So 0 plus 1.875 will give you 1.875. So you will continue this process until this residue, the largest residue, approaches to 0. So the iteration to these examples are listed in tabular form. You can have a look. So in first iteration, your residues were that I showed you earlier, 11, 10, minus 15. So the initial guess was 0, 0, 0. So this was the largest one. Divided with the diagonal entry, you will get this dx. So in next iteration, this initial guess will be, or the next iteration will be 0, 0, and this will be changed in x3. Since this was R3, change in x3, make it 1.875. And then you will find again the residuals. So these are the three residuals. So the largest one is this one. So you will repeat that process. You will divide the largest with that diagonal entry since this is in the first residue, in the first column. So you will divide this with A11. So you will get this value. So this is changed in first. So your x1 now will be changed. 0 plus this dx will make it 1.5288. This is your new guess. So we're continuing this process in the similar way. You will reach after 8 iteration to these answers. So your x1 means your latest approximation will be, if you look at these two iterations. So this x1 in the 7th iteration here it is same. So this is 4 decimal accurate. In the similar case, this is same. So 4 decimal accuracy here. This is 2 decimal accuracy because this is 196019. So it's giving less than 0.9. So the whole result is actually 1 decimal accurate, or in fact it should be 2 decimal accurate since all these, this is 4, this is 4, this is 2. So you will be having 2 decimal accuracy. So the final solution to the given system will be this one. So this is what you can do more rapidly if you choose the optimum value for the relaxation parameter in such a way that this is the largest value and you calculate the increment. So then you can solve, or you can find the system with less iterations and more accurate. You can try this is, take this one as an assignment. So solve the similar system with the help of Gauss Siedel method, and then with this relaxation method, and then compare the results. So you will see the difference. Thank you very much for your attention. Your questions are welcome. So here are the links where you can contact me. So post your assignments in your Google Classroom and post your questions there, or use any one of the forum to discuss or to ask any of your questions. Assalamu alaikum. Allah Hafiz.